Hello, everyone. Today I'm going to be talking about friction. Now, we've covered a bit of friction so far. However, we're going to be talking about in more detail on how friction works and how we will be calculating it. All right. So, to start off with, just the general definition of friction that we already know, it's the force that opposes the sliding between objects. So, as you slide something on the ground, it will always be pointed in the opposite direction of the motion, trying to fight back. It's important to note that that will always be it'll be parallel to the surface. So, if you're on a flat level surface, like you are most of the time, it's simply pointed in the opposite way you're going. However, if you're going up or down a ramp, it'll be pointing up and down the ramp parallel to however the floor is situated. Now, there's two types of forces that we're going to be talking about. The first of which is static friction. Static friction is the force exerted on a surface when there is no motion between the objects yet. So this happens when you start to push an object, but before it actually gets to start moving, you are encountering static friction. So sometimes with heavier objects, you'll notice you have to give it a big shove, and then once it starts moving, it gets a bit easier. Static friction is a big part of that, opposing the motion. On the other hand, we have kinetic friction, which is the friction between objects where we have relative motion, so things are moving. So static friction could be seen with a block sitting on a ramp, while kinetic friction would be the friction on a block as it slides down the ramp. They're slightly different from each other. The big relationship between the two is static friction is always greater than the kinetic friction. Now, I first realized the difference between static friction and kinetic friction. I distinctly remember it. I was the passenger of my mom's car when I was a kid, and I left a sheet of paper up on the dash in front of me. And as it was, staying there just fine, my mom turns on the car. The whole car starts to vibrate, as cars tend to do. And that changed the static friction of the paper, because nothing was moving, into kinetic friction, because the car was vibrating. And because kinetic friction is less than static friction, it caused the whole paper to slide down the dash, and then I had to catch it. So the kinetic friction is less than the static friction, and it takes over whenever something starts to move. Now, find friction at a constant velocity. A very common relationship that we see being talked about in questions is, and in the real world, as you push something and you're pushing it so it's moving at constant velocity. The reason why you're able to do that, the reason why you're not constantly accelerating like one would expect, is because friction is fighting against you. So as you push and friction pushes back, you end up moving at a constant velocity as you get things sliding. If you're pushing any faster, speed up or slow down, depending on how fast you're pushing it. But if you are in perfect balance and you're pushing at the same amount as friction, you're moving at constant velocity. Now, the reason why this is important is this is commonly asked where you're given a situation where I'll give you, let's say, the applied force. I'm pushing it at 200 newtons one way. It says it's moving at constant velocity, and it asks, okay, what's the friction? You have to know if I'm moving at constant velocity, my force going one way has to equal the friction going the other. There's no net force. We're at equilibrium when we're balanced out. All right, coefficient of friction. Now let's get into actually calculating our friction. So the frictional formula is going to be this right here. The force of friction is equal to this new letter, which is the coefficient of friction, times the normal force. So friction is related to how much the ground is pushing up on the object. Now this letter right here is the letter mu. It's a Greek letter. It kind of looks like a U, but it has that extra little line in front of it. Now, this particular text happens to stylize and make it almost look like a teardrop, but it's just a line in front. So just, up, down, and back kind of thing. Nothing too complicated there. So this is the coefficient of friction, which is just the ratio or how strong friction is between the object. So the more friction there is in an object, the higher the coefficient of friction is. And as I said, it's related to the normal force. In most problems and in most situations, the normal force is simply going to equal the weight of the object. If we remember drawing our free body diagrams, we often see our weight going down and our normal force going up the same length. And that's going to be true in most problems. Really, the only case of a friction problem where it's not going to be true is if we're on a ramp. If we're on a ramp, then gravity is going to be more than our normal force. And they're still related, we can still calculate them, but they are different from each other. So just keep that in mind. So gravity and normal force, often the same if we're on a flat level surface. Over here, we have just two examples. We have two boxes. This one has a greater weight. It's a bigger object. You can see that also has a greater normal force. Because it has a greater normal force, it has a greater friction. Now, on the front of the reference tables, we actually have a list of the coefficients of friction. So this is the front, bottom, right of the reference table. You can see it's broken down in two sections: the kinetic, which you're going to use anytime there's motion, and the static, anytime you're going to use when it's still standing still. You'll notice that static's missing some. It's because static friction with liquids, so wet objects, wet ice, and then also Teflon as well. There's a little bit more fancy physics going on than just this formula, so we just ignore them. And we're only focusing on mainly these particular objects. So, for example, dry concrete has more friction than wet concrete. I think that should make sense. Wax skis on snow has a very small amount of friction. Again, makes sense. And then steel on steel has a very high amount of friction. I mean, not the highest, but a decently high, which may surprise some people. But here are all our kind of values for friction. You will notice that there's no units on these. This mu right here, this coefficient of friction, is one of two numbers or two variables in this class that do not have a unit. So it is a unitless number. And that often makes people get nervous and make mistakes because they want to put units on them. The reason why it's a unitless number is because it's a ratio between two forces. Remember, on the left side, it's newtons, so the right side also has to equal newtons. And if you were to make any units here, it would mess it up. So it's simply telling you the ratio of how strong the friction is in comparison to the normal force. It's a unitless number. I think that's pretty much all I want to say. Again, kinetic is when motion's happening. Static is when there is no motion. You'll notice that static is always greater than the kinetic, which is what we mentioned before. Surface area. So before we get into some example questions, one easy misconception to fix, a lot of people don't have problems with this, is surface area in relation to friction. Force of friction is independent of the surface area of the ground, which means it has no effect on it. The reason's pretty simple. So even though it's contacting the ground less over here on this left example, every point of contact has more normal force to it. More weight is bearing on it, so that basically evens it out. Over here, we have more points of contact, but overall there's less weight per point of contact. So the surface area is independent of it. They balance each other out. All right. Friction problem 1. I apologize I had to cross this little out. I kind of left it. We're going to use 0.2. But anyways, let me walk you through an example friction problem. We are... I'm not going to write on the screen, so I'm just going to talk you through it. So make sure you're kind of paying attention to it. So in order to start a friction problem, we can see that we're given a decent amount of variables. That's very common in a friction problem. You tend to be given too many things because, frankly, this is a pretty easy formula to use. So they want to make sure you know what things we should be talking about. So in this case, we have a 50 kilogram block that's being pulled by 100 newtons force. And then we're given the coefficient of friction of 0.2. And we're asked to find how much is the force of friction going back. So in order to solve this, the first thing we need to do, because we have the coefficient of friction, we need to find the normal force. Now, because we're on a flat level surface, which most of the time we're going to be, the normal force is equal to the weight. I have the mass of it. Remember, mass and weight are different. I have the mass of it. I need to convert that into the weight using the formula G is equal to Fg over m, which is going to end up being 50 kilograms times 9.81. I'm going to simplify that to 50 kilograms times 10 meters per second squared, which is 500 newtons. So I have 500 newtons of weight, which is 500 newtons of force. And all I do is take the 0.2, multiply it by the 500 newtons, and we get the friction from that. So 0.2 times 500 is 100. So we have 100 newtons of friction going to the left. The two forces are balancing each other out. So interestingly enough, we're moving at a constant velocity here. That's how you do one of these formulas. You just need to find the missing part, and keep in mind that normal force and weight are often directly related to one another. Here's another one. We have the same exact relationship. We have a couple of different forces given to us, and we're asked to find the coefficient of friction. Again, one of the challenges of this is making sure you pick the right force. So, the right forces. So the frictional force is this 100 newtons. The normal force is going to be equal to the 400 newtons because gravity and normal force equal in opposite direction. They're the same as each other because we're on a flat level surface. So it's going to be 100 is equal to mu times 400. So mu is simply 100 divided by 400, 0.25. Again, it's a unitless number, so I just leave it as 0.25. And that is pretty much it. Friction problems, I've been waiting to give you most of the Newton's law problems until we covered friction. At this point, we're going to start practicing types of problems where we have to draw free body diagrams, where we have to see what's going on, make sure we understand the relationships between different things, like gravity and normal force are often the same, or the force going to the left and the force going to the right have to be the same if we have no acceleration. Or given the acceleration and one of the forces, we can find the other one by using the net force. All these different things come into play, and frictional and the force of friction is very important into this in these types of problems. So we're going to be practicing quite a lot of these problems in the future, whether they directly involve this formula or not. Sometimes they'll just simply involve knowing the relationship between friction and the applied force, if we're moving at constant velocity or not. That's it for this video. Hope you have a good day.